Recursion. You've probably heard the term. And yeah, it can sound a little intimidating, but it's actually one of the most elegant and powerful ideas in all of programming. So let's dive in and demystify this thing together.
Just take a look at this fractal. See how each branch of the tree looks like a tiny version of the whole tree? And the branches on that branch are even tinier versions? This idea, this beautiful pattern of self-similarity, that's the heart of recursion.
So that gets you thinking, right? What if we could take that same idea from nature and apply it to our code? What if a function could actually call itself to get a job done?
All right, so first things first, let's really build our intuition for this. We're going to start by looking at how this pattern of defining something in terms of itself pops up all over the place, even outside of computers.
Think about it. These definitions just feel natural, don't they? A human comes from another human. A folder on your computer can hold other folders inside of it. A fractal is made of smaller copies of itself. In every single case, the thing we're defining is part of its own definition.
And that brings us right to our formal definition for programming. Recursion is just this. It's a way of solving a problem by breaking it down into smaller, simpler versions of the exact same problem.
Okay, so how do we actually build one of these functions without having it just run on forever? Well, it turns out there are two simple, absolutely essential rules you have to follow.
Here they are. Number one, you need a base case. Think of this as your escape hatch, your stop sign. It's the simplest possible version of the problem, the one you can answer directly without calling the function again. Then you have the general case. This is the part that does the actual work of making the problem smaller and then calling itself to solve that new, smaller piece.
And what happens if you forget that stop sign? Well, you get into big trouble. It's called infinite recursion. The function just keeps calling itself over and over and over with no end in sight until your whole program just crashes. So the big takeaway here is you always need a base case, no exceptions.
All right, enough theory, right? Let's see this in action with probably the most famous example of recursion out there, the Fibonacci sequence. It's a classic for a reason. It's just a perfect way to see how this all works.
And just for some fun background, this isn't some random problem cooked up for a computer science class. It was actually invented by a mathematician named Fibonacci way back in the 13th century. He was trying to model how rabbit populations grow. Kind of cool, huh?
So here is the sequence itself. The pattern is pretty simple once you see it. Each number is just the sum of the two numbers that came before it. See? 2 is 1 plus 1. 3 is 1 plus 2. 5 is 2 plus 3. And on it goes. This structure is just begging for a recursive solution.
Okay, so let's get our hands dirty. How would a function actually figure out the fourth Fibonacci number? We'll call it fib4. Let's trace exactly what happens.
So to get fib of 4, our function knows the rule. It needs to add fib of 3 and fib of 2. But wait a second, it doesn't know what those are yet. So what does it do? It calls itself twice. Once for fib of 3 and once for fib of 2.
And this is where you can really see the recursion unfold. The call to fib of 3 on the left has to break itself down into fib of 2 plus fib of 1. And the call to fib of 2 on the right breaks down into fib of 1 and fib of 0. With every level we go down, the problem just keeps getting simpler. And here we go. We finally hit our base cases. We pre-programmed our function to know that fib of 1 is 1 and fib of 0 is 0. These are the simplest possible questions we can ask, the ones with direct answers. These are our stop signs. No more recursive calls needed from here.
So once those base cases return their simple values, the ones and zeros, the answers start bubbling back up the chain. They get added together, those sums get passed to the level above, until finally, we get our answer for the original problem, fib of 4, which is 3.
Now, as you just saw, recursion can produce solutions that are incredibly clean and, well, elegant. The code often reads just like the definition of the problem, but that elegance can come with a pretty significant hidden cost. Here's the trade-off you always have to think about. On the one hand, the power. You get code that's often really simple and easy to read, but the cost? It can be slow and chew up a lot of memory. Think about our Fibonacci example. It was calculating the same values over and over again. That inefficiency leads to what's called exponential time complexity, which basically means it gets slow fast as the numbers get bigger. Now that you've got the fundamentals down, the absolute best way to really get good at this is to start trying to think recursively yourself. So let's look at a few challenges for you to chew on. Here is some classic problems that are just perfect for recursive thinking. How could you find the factorial of a number if you already knew how to find the factorial of a slightly smaller number?
Or how could you solve the famous Tower of Hanoi puzzle by first solving it for a smaller stack of disks? Give it some thought. So, that's our deep dive into recursion. I'll leave you with this final thought. Now that you have this new mental model, where else do you see it? What everyday problems, maybe not even related to coding, could you reframe and solve by breaking them down into smaller pieces of themselves?